first thing that I would like to talk about today is transconductance. So MOSFET transistors are used in analog circuits to convert an input voltage, VGS, into an output current, ID. Transconductance is a measure of a MOSFET's ability to perform this conversion. Mathematically, transconductance is given by the symbol GM, and it is simply the derivative of the drain current with respect to that input gate source voltage while holding the quantity VDS constant. So we know that in the triode region, drain current ID, I'm going to look at my notes so I don't make some asinine mistake here. Is given by mu n C ox W effective over L effective times the quantity VGS minus VTH, I'm sorry. Multiplied by VDS minus 1/2 VDS quantity squared. Or, no, go away. VDS less than or equal to VGS minus VTH. So from this, our transconductance is just the derivative of this with respect to VDS. So it should be fairly straightforward to see that we have this constant term out front times VGS minus VTH times VDS. So when we take the derivative, this VDS is going to go away. And then we have that same term multiplied by this constant value of 1/2 VDS squared. So that whole thing is going to go away. And all we're left with in the triode region is mu n C ox W effective over L effective times VGS minus VTH. I'm going to need somebody to remind me. Get a shim to make me stop wobbling like this, or I'm going to go insane. More so than usual. All right, so in the saturation region, we know that ID is equal to 1/2 UN Cox W effective over L effective times VGS minus VTH quantity squared. Right? So when we take the derivative of this guy with respect to VGS, we get UN Cox W effective over L effective times VGS. Sorry, let me erase that. Minus VTH. All right. There are some alternative definitions. These are all the exact same, represent the exact same thing mathematically. It's just a little bit easier to find transconductance depending on what information that you are given. So another way that we could express this transconductance is the square root of twice UN Cox W effective over L effective times our drain current ID, or if for whatever reason we don't know the mobility and oxide capacitance, we could express this as twice ID divided by VGS minus VTH. Sorry, I need to put for VDS greater than or equal to VGS minus VTH here. So we have different transconductance relationships depending on whether or not we are in saturation or triode region, and that depends or is dependent on the fact that we have different current relationships in those regions, right? Nothing wild or crazy there. In the event that channel length modulation effects are present, we have mu n Cox W effective over L effective times VGS minus VTH times that channel length modulation addition, 1 plus capital lambda VDS minus VDS that. Or alternatively, square root of twice mu n Cox W effective over L effective ID divided by that quantity, 1 plus capital lambda VDS minus VDS set. So I'm going to ask you guys what I hope is a very easy and obvious question. The channel length modulation transconductance is only valid during triode, saturation, or is it valid for both? Saturation only, right? Why is that? Channel length modulation only occurs under saturation, right? For channel length modulation to occur, we need to be in pinch off and then making the channel shorter. And by definition, triode region does not cause pinch off to happen, right? So the channel length modulation relationships only occur when we are in saturation. So I'm going to be real clear about that because I've seen people not understand that in the past. All right. So while we are on the topic of transconductance, let's now talk about body effect transconductance. So since a potential difference between the source and body of a MOSFET has an effect on the quantity VTH, our threshold voltage. We talked about this, I think it was yesterday, no, Monday, when we talked about body effects. Body effect also influences the overdrive voltage VGS minus VTH. And since our drain current in both the saturation region and the triode region depend on the quantity VGS minus VTH, body effect influences current flow, and therefore it will have its own transconductance. So our body effect transconductance mathematically is going to be represented by the symbol GM for transconductance, and then we tack a little B on there at the end to let us know that we're dealing with body effect. And it is defined to be the derivative of the drain current with respect to the body source potential. And so that will look like mu n Cox W effective over L effective times the quantity VGS minus VTH times negative the derivative VTH with respect to VBS. So since the derivative of VTH with respect to VBS is negative the derivative of VTH with respect to VSB. So just to be clear here, all I am saying is that if we change the order of our subscripts, so if we look at the body source potential, that is the exact same thing as the negative of the source body potential, right? So when we flip the subscripts, it's introducing a negative sign, right? So if we take the derivative of our body effect relationship for on our threshold voltage, we wind up getting negative 1/2 gamma times twice IF plus ESB, all of this to the -1/2 power. And substituting in this relationship, we find that our body effect transconductance is simply our transconductance multiplied by gamma, our body effect coefficient, divided by twice times the square root of twice phi f plus ESB. Okay, so now, before we get into entirely new things, I would like for us to revisit and refresh ourselves on our small signal models, because that is going to be such a critical part of our analysis of actual amplifier devices, as those of you who suffered through 335 and 336 found out. It's 80% of it is screwing around with those small signal models and figuring out what the hell is going on. So small signal models are used to analyze variations around a DC operating point for a MOSFET. Albert, I'm going to pick on you, not really pick on you, but ask you a couple of questions, okay? Because I'm well aware of the backgrounds of everybody else here. Did you have to take Circuits 1?
Yeah.
Okay. Did you take it with me? I feel like you might have. I thought so. Like probably 3 years back or 2 years back or so. Yeah. Yeah. Been a minute. Do you remember anything about when we were talking about like linear circuit elements and all that kind of crap? Arguably rings a bell. Hopefully it arguably rings, or a little more than arguably rings a bell for the rest of you. So our current voltage relationship, whether we're in the triode region or the saturation region for our MOSFET, we have what's called a nonlinear relationship, right? So for a resistor, the resistance is simply the constant of proportionality between the voltage and current, okay? For a capacitor, it's not that simple. There's either a derivative-based relationship or a relationship, depending on if we're trying to convert voltage to current and current to voltage, and the same exact relationships for the capacitor. They're just in inverse. We covered all of that back in Circuits 1. Well, these transistors and their nonlinear range of operation makes circuit analysis with them particularly difficult. So what we do is we try to force them to be linear by looking at them at a DC operating point and then just looking at small variations around it, where we say that those small variations are approximately linear. So we get to apply those linear circuit analysis techniques that we learned way back in Circuits 1 and all that kind of stuff to these kind of terrifyingly complex systems, okay? So these small signal models, which is, I think this is probably your first time being introduced to anything like this, are the electrical engineers' ways of forcing these nonlinear circuit elements to behave like linear circuit elements that we can kind of wrap our heads around. So yeah, so this is where the hell these things are coming from, effectively, is what I'm trying to impress upon you, okay? So for a basic MOSFET, we have the following model. So our gate terminal is over here on the left, our drain terminal is over here on the right, our source terminal is down here at the bottom. And between our gate and source, we have an open circuit where we have our small signal voltage, which I'm going to denote by using lowercase letters, a VGS. So this is some subtle variation or oscillation around our DC VGS that we use to bias this thing. And what we get out of this system is GM, our transconductance, multiplied by our VGS. So effectively, the current that flows from the drain to the source is simply the transconductance, which is all about converting that input voltage into a current, multiplied by the voltage that causes the current to be created. Nothing wild or particularly wacky there. Okay, so this model just represents, we have an input voltage, and then it gets transformed to a current at the output by a dependent current source. It's literally why we use dependent current sources in circuits 1. If these things didn't exist, we could throw them away, and I'm sure all of those students would be so much happier. But doesn't pan out for us. Okay, so this is how things look for an ideal MOSFET. And for the overwhelming majority of these guys in here, this is what we dealt with for most of 335 and 336. Okay. Now, with channel length modulation effects present, we have to modify things, right? So we still have our small signal voltage VGS. Shouldn't be a terminal there. Here's our source. Still have our GM VGS here. Now we are going to model the effects of channel length modulation by introducing a resistor. I think the textbook that we are using calls it R out, but I want to say that back in 335 and 336, we just called it R not, right? Lowercase r not, where this resistance value is simply the derivative of VDS with respect to our drain current, or 1 over 1/2 mu n C ox W effective over L effective times VGS minus VTH squared times, sorry, this should be capital lambda, not lowercase, or to make our life a little bit easier, approximately 1 over lambda times our DC drain current. Okay, and then, sorry, I forgot to include this over here. Here's our drain. And we had to include this output resistance for some of the stuff that we did in 335 and 336. So let's go ahead and screw everything up and include body effects now too. See what our small signal model will look like. So we're going to have our dependent source here, VM, VGS, and all that kind of good stuff. Now between our source and our body though, so let's put our body terminal down here. We are going to have some voltage, VSB. We have our channel length modulation resistor R out. And then, oh, sorry, this should be a dependent source. My apologies. We're going to have another dependent source, current source, GMB times VSB, that is influencing our output current relationship. Okay, so this guy is MOSFET with CLM and body effects. And this guy up here, model with MOSFET with just channel length modulation. So I want to say that I might have introduced this small signal model in 336 to my class, but I don't think we ever got around to using it. We gotta deal with stuff now. We're seniors, so we got other stuff to do. All right, so we're not quite ready to get into our analysis. That's what we're going to start doing next week. So the next things that I want to talk about are some other things that will be of particular interest to us, particularly sub-threshold operation, and then some short channel effects. So, sub-threshold So previously, when we talked about where the threshold voltage arises from, we said that the channel that shows up between the drain and the source of a MOSFET transistor occurs when VGS is equal or greater than or equal to VTH, right? So we effectively said strong inversion needed to occur for any current to flow. Well, that's not entirely true, okay? In practice, the MOSFET doesn't change states either. The channel doesn't go from it not being there to immediately it being there. It's a much more gradual transition. And so for small values of VGS, minority carriers can be attracted to the area below the gate, enabling sub-threshold operation. Okay, so when VGS is less than VTH, minority carriers can experience weak inversion and may diffuse from the source the drain. Okay, so let's think about that for just a moment, okay? What does the FET or FET stand for in MOSFET? Anybody remember? Field effect transistor, okay? So that means that it's the presence of an electric field that drives our current, right? So effectively, in a MOSFET under normal operation, everything is based on drift, right? Carrier drift. We apply an electric field which imparts a velocity on the carriers and they move. That's drift. Now we have something that's based on diffusion, right? So in sub-threshold operation, our MOSFET current is effectively due to the same reason that BJTs have current. It's diffusion of charge carriers across those PN junctions, all right? So we have a very BJT-like operation, but we do not have a BJT-like construction, okay? So if you recall, in a BJT transistor, we have a base, a collector, and an emitter, right? And the level of doping concentrations, as well as the physical size of those regions, are vastly different between those three areas, right? So our emitter, where our charge carriers come from, typically have extremely high concentrations. And our collectors, where our charge carriers go to, have much, much lower concentrations than the emitter. And our base is kind of somewhere in between. But for the BJT that's formed by this weak channel, we actually have identical concentrations between our collector and emitter and a base that's very weakly doped. So we are not going to see the levels of current, like the magnitude of current that we would see with a typical BJT, which should be somewhere on par with that of a MOSFET. So tens to thousands of microamps would be a typical range for a BJT and a MOSFET transistor for a general application. So in a BJT, sorry, let me circle back around here. Carriers are emitted by the emitter. Diffuse across the base and are collected at the collector. In a sub-threshold MOSFET, the carriers are emitted by the source diffuse across the body underneath the gate oxide and are collected at the drain. So mathematically, our drain current is going to look something like this. We're going to call this ID off. It's kind of playing the role as our reverse bias saturation current density did in our BJTs, or really kind of our PN junctions, times W over L times the exponential of Q times VGS over N times KBT. And actually, it's going to make no difference to you guys really, but I'm not going to call that N, I'm going to call that eta. So Greek looking N, so that it doesn't mean concentration. And typically speaking, our drain source voltage needs to be about 200 millivolts or more in order to cause some sub-threshold current to flow. This quantity ID off is going to be around 100 pico amperes. Okay. So this current is, by an order of magnitude or so, about 1,000,000 times smaller than what we would expect our drain current during normal operation to be. But then it exponentially increases depending on how much extra VGS voltage we apply, right? And eta is about 1.6 for most CMOS processes, and it represents a non-ideality factor. When we learned about the current flowing through a PN junction, it looked something pretty similar to this, where it was trying to remember exactly off the top of my head. Very similar exponential thing, and then the denominator there was it was just a number 1 effectively for us, and that was because the PN junctions that we were dealing with were all based purely on what we were looking at of step junctions, right? And then in truth, there should have been a non-ideality factor there for PN junctions. For whatever reason, it's typically called M, that ranges between 1 and 2, depending on if we have, like what type of junction we have. Well, this ideality factor here is effectively doing the same thing. It's just slightly skewing that exponential function to either rise more slowly or more steeply, depending on how ideal or non-ideal the process is. That's all this thing is. Okay. So if we plotted our drain current, this is the log of our drain current, and let's call this guy 10 to the 6th, excuse me, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, 10, 10 to the minus 11, there we go. On this axis, we plot VGS. Way out here, we'll have VDD, And about right here, we'll have VTH. What we should see, something that looks like this. So it's going to exponentially grow. I'm going to try to draw this as least crappily as I can. When we get in the range of VTH, kind of tapers off. And then over here, we have effectively triode region operation. And so over to the left here, we have weak inversion. Over to the far right here, we have strong inversion. Kind of in the middle here, as a transition, we could call this moderate inversion. So this moderate inversion region is where our overdrive voltage is very, very small, right? So we're not beyond, we're not fully driving this guy by any stretch of the imagination. This thing right here, we'll call our sub threshold slope, is important. So if we take the log of both sides where we express, so when we write this out, with KBT over Q being equal to our thermal voltage VT, what we find is that the log of our drain current is equal to the log ID off plus the log W effective over L effective plus 1 over theta VT times the log of Euler's number E multiplied by VGS, where this guy right here is our subthreshold slope. Let me give you guys a minute to write that stuff down. All right. We have a little under 30 minutes left, so let's talk about short channel effects. So the first short channel effect that I want to talk about is what's called carrier velocity saturation. So when we were deriving the current voltage relationships for our triode region operation, we made an assumption that our carrier velocity v was equal to, I think it's mu times, yeah, v is equal to u times e. And we could rearrange this relationship and say then that our carrier mobility is simply our velocity divided by our applied velocity. Okay, so this is the assumption that we made. In truth, mobility and electric field are not necessarily linearly related like what it looks like here. Okay, so in practice, if we apply a very, very large voltage VDS, what are we doing? We are imparting a whole heck of a lot of energy to electrons in the source, flinging them at the drain as fast as we can. Okay, so let's think about what that means. If we are imparting a lot of kinetic energy into our electrons, they are going to strike our lattice structure with more energy, which causes lattice vibrations. And the more electrons we fire at the speed, the more vibrations we see, the more scattering events that occur. And so we'll find that our electrons that are trying to make their way from the drain, from the source to the drain, are not able to speed up because they're having so many interactions with the lattice itself, right? And they're occurring so frequently that they're not giving enough time to accelerate. So if we plotted drift velocity as a function of electric field, this is going to be E, so let's call this electric. In centimeters. Trying to not turn my computer, but write centimeters per second. What we're going to have is something that looks like this. So this is 10 to the 7, 10 to the 6. Down here will be 10 to the 5, and then 10 to the 2, 10 to the 3, 10 to the 4, 5, so forth. So for electrons, see something like this. Pretty linear relationship. And once we pass a threshold, it kind of flattens out. And we're going to see something extraordinarily similar for holes. I really wish I could draw a straight line. So this value here is what we're going to call the critical value for the field. And so effectively all this means is that when we apply some VDS voltage that's too high, our charge carriers are going to slow down. So we're not going to see, it's going to negatively impact the performance of our device, such that our drain current, ID, will be W times our saturation velocity times our oxide capacitance multiplied by VGS minus VTH minus VDS SAT. Okay. So we start to see our drain current taper off and decrease as it's larger and larger and larger. And it's because we are seeing the frequency of our traveling electrons striking the lattice and causing those interactions. All right. We have another potential short channel effect called carriers. So in very small devices, some carriers drifting near the drain can obtain energies much greater than the thermal energy of carriers under equilibrium conditions. These carriers are called hot carriers, okay? So we have a similar kind of situation here as to what we just talked about with velocity saturation, except that the problem with these hot carriers, so we were imparting a lot of energy into these electrons as they're trying to go from the source into the drain, right? The ones that make it all the way across the way hit those lattice vibrations and all that kind of stuff and wind up slowing down. But what if one of them hits a lattice vibration funny, fires up into the gate oxide? We start winding up doping our gate and causing it to electrically break down, right? Our oxide, or not, we don't fire it into the gate, we fire it into the oxide, right? The oxide is a big neutral barrier that prevents current from flowing through the gate and influencing the behavior of the device, right? That's why we get that very nice and neat kind of switching operation and all that kind of good stuff. If we start effectively doping that oxide, what happens? Our input resistance, which is how, right? So we treat, I'm directing this mainly towards Albert because I don't know whether or not he knows this. So we treat the gate body connection as effectively a capacitor. I think we've talked about that in this class, but so what that translates to for our models is that we can look at this as an open circuit, right? An infinite amount of resistance. So our input signals see this infinite impedance, and that's what allows us to bias everything nicely and neatly and makes all of the drain current flow down through the source, right? As soon as that oxide starts getting doped it starts becoming electrically conductive. And an electrically conductive path means that some portion of our drain current gets steered off and is able to flow into or out of the gate. So we are losing the control that we have over the device's operation, right? So that's what hot carriers do. Now, what happens with the presence of those electrons in the gate is that it tends to thermally degrade the oxide layer itself as well, so that over time, our device begins to break down to such a point to where it effectively overheats and we no longer have a working transistor either. Okay, so those are kind of two different effects that are related to hot carriers. So think about it as avalanche breakdown for transistors as opposed to avalanche breakdown for PN junction. We get a cascade of effects that ultimately wind up causing the device to overheat and destroy itself. So, all right. I think the last thing that we're going to talk about today, and it's the one that I know the least about, so that's why I'm going to not talk about it a lot, is drain-induced barrier lowering. So in small channel length, MOSFETs, unintended electrostatic interactions can occur between the source and the drain. Known as drain-induced barrier lowering, or DIBBLE. So what happens is positive potential at the drain helps to attract electrons underneath the gate oxide, resulting in the DS affecting ETH. So let's think about that, okay? So if we have a very, very short channel area, meaning that the area below our polysilicon gate is small, if we apply a very, very high potential to our drain, it starts acting as almost a second gate control, okay? It starts pulling minority carrier electrons from our body and starts bringing them up, trying to form the channel itself, okay? Which is extraordinarily bad, because if we don't have that gate control, we don't have a transistor anymore, right? So that's what drain-induced barrier leakage is. So effectively, what has happened is that As our technology nodes get smaller and smaller and smaller, the amount of voltage or the size of the signals that we can apply to our system have also gotten smaller and smaller and smaller, right? So for a C5 process, which is what we're designing things around, the minimum acceptable size of our channel length is 2 lambda, right? It's practically always going to be 2 lambda, but for a 300 nanometer process, that means we're looking at 0.6 microns. So pretty small, but not wildly too small. And we can put voltages of up to 5 volts and not see anything like this occur. Well, when we get down to our 180 nanometer processes and all that kind of stuff, that maximum voltage that we can apply drops down to somewhere close to 3.3. And when we get down to like 14 nanometer processes, we can only put like 1 volt on our drain. So before we start losing gate control of our devices and all this kind of stuff. So that's one of the biggest drawbacks or one of the biggest reasons why we can't make our technology nodes smaller and smaller and smaller anymore is every time we make it smaller, we are lowering the amount of signal that we can put on, which means we're losing resolution as to what we can see, right? Another issue not covered in our textbook or anything like that is the smaller and smaller and smaller the things we make, the effects of heat transfer become more and more and more prevalent because we are approaching places where the thermal voltage is on the same order as the signals we're looking at. So how do you tell the difference between Brownian motion and you actually trying to send a signal through this thing? So anywho, that's enough out of me for today. So on Monday, I think we're going to start getting into analysis stuff.